What does a technical system do when time is short, attention is limited, and the consequences are real? In 1969, an Apollo computer helped guide a lunar landing through an unexpected overload. In 2016, AlphaGo surprised the world's best players in one of humanity's oldest strategic games. These events are often told as steps toward machine autonomy, but that story is too simple. Apollo and AlphaGo were built for very different worlds. Their real lesson is not that people became obsolete. It is that powerful systems change the conditions under which people must exercise judgment. Apollo 11 was never a story of one pilot, one computer, or one moment of genius. It was a vast collaboration. Astronauts in the lunar module, controllers in Houston, engineers who had designed and tested the guidance software, and mission procedures built over years of rehearsal. The Apollo guidance computer had extremely limited memory by modern standards, yet it was designed for real-time work under severe constraints. Its task was not to understand the moon or decide humanity's future. Its task was precise: calculate guidance and control functions within a carefully defined mission. During the lunar descent, the guidance computer displayed the famous 1201 and 1202 program alarms. They signaled executive overload. Recurring radar-related jobs were consuming temporary scheduling resources. The computer did not simply choose to land. Its operating system had been designed to protect the most important work. It restarted, preserved selected critical functions, and did not restart the erroneous lower priority tasks that had helped cause the overload. This recovery behavior was the result of engineering, testing, and foresight long before the lunar module approached the surface. That distinction matters. A system can be designed to protect a priority and still not determine the purpose of the mission. The Apollo computer could resume essential guidance work because its designers had specified what counted as essential. Mission control could judge that the restart behavior allowed the descent to continue because engineers understood what the software had been built to do. And the crew remained active participants in the landing. Apollo was not an autonomous machine replacing people. It was a distributed operation in which human judgment and automated recovery had to work together under pressure. The achievement of Apollo was not the disappearance of uncertainty. It was the disciplined management of uncertainty. Simulation, testing, and procedures made the mission safer, but they did not create a perfect digital copy of the moon or remove the need for improvisation. The value of the guidance system was that it made some problems tractable at the moment they mattered most. It narrowed attention without abolishing responsibility. That is a durable model for automation. Define a bounded task, test failure modes, make priorities explicit, and keep people able to understand and act when conditions change. Nearly half a century later, AlphaGo confronted a very different problem. Go is played on a simple board with black and white stones, but its possible lines of play are extraordinarily numerous, and its positions are difficult to evaluate. For decades, the game challenged computer researchers because naive search alone could not capture the strategic character that expert players recognized. In March 2016, AlphaGo faced Lee Sedol, one of the world's leading Go players, in Seoul. The match became a landmark, not because a machine had become human, but because a specialized system performed at an astonishing level in a demanding domain. AlphaGo did not win by checking every possible game to the end. Its designers combined several methods. Policy networks suggested promising moves. Value networks estimated the strength of positions. Monte Carlo tree search explored lines of play. The system learned first from expert human games and then through self-play. Together, these methods made it possible to focus search where it was most useful. This was a major technical breakthrough, but it is important to name it accurately. AlphaGo was a trained, goal-directed game-playing system operating within the explicit rules and objective of Go. In the second game, AlphaGo played the move now known as Move 37. To many commentators, it looked deeply unusual. DeepMind later described it as an inventive move with a very low predicted likelihood. The point is not that AlphaGo felt inspiration or discovered a hidden soul within the game. The point is more interesting. Its combination of learned evaluation and search produced a move that expert observers did not initially expect, and the move proved strategically powerful. Surprise is not proof of consciousness, but it can reveal the limits of our own habits of seeing. The match was not a simple story of human defeat. In the fourth game, Lee Sedol played move 78, another exceptionally unlikely move by AlphaGo's own predictions. It helped create a position in which AlphaGo made a decisive error, and Lee won the game. Fans later called the move God's touch. The name captures the emotional force of the moment, but we do not need to turn it into a myth about irrational human courage defeating cold calculation. Lee Sedol was an expert, making a remarkable move in a living competitive situation. The game showed both the strength and the limits of a specialized system. Apollo and AlphaGo belong to different histories. Apollo's guidance computer was engineered for bounded, real-time control in a safety-critical mission. AlphaGo was trained to play a closed strategic game with a clear scoring objective. One system recovered from a known kind of overload. The other generated high-performing moves in an immense search space. Neither case leads automatically to the other, and neither proves that technology is destined to rule over people. The comparison becomes useful only when it teaches us to ask better questions about objectives, limits, testing, interpretation, and the place of human oversight. Today, algorithmic systems can rank information, recommend options, classify patterns, and support decisions in institutions. Their effects are real, but they are not forces of nature. Every system has designers, data sources, objectives, operators, and people affected by its outputs. That is why responsible AI is not only a technical problem, it is a question of governance. Who defines success? What risks are measured? When can a decision be challenged? Who remains accountable when a recommendation causes harm? Technical capability can widen our choices, but it cannot decide which choices are worthy. The lesson of Apollo 11 and AlphaGo is not that humans must defeat their machines, or that machines will inevitably surpass their makers. It is that a system's power depends on the purposes, boundaries, and institutions around it. Apollo succeeded through engineering resilience, joined to human coordination. AlphaGo showed that learned systems can make experts look again at a familiar domain. Our task now is to build systems that remain answerable to people, not because people are flawless, but because responsibility, care, and judgment cannot be outsourced to a score. The future of autonomy is still a human decision.